parametric equations provide a very convenient way for calculating the length of a curve. So let's draw a particular curve, and since we're using parametric equations, this curve need not follow the vertical line test. It doesn't need to be a function y, it does not need to be a function of x. All right, and so here we have a curve, and let's suppose that this curve starts at t is equal to a and t is equal to b, and we have a pair of parametric equations, x of t, y of t, where they are both defined between a and b for t, and we just are tracing this out along the curve, starting at a, going to b. And the assumptions here are that x and t are differentiable, their derivatives are never going to be zero at the same time, and this tracing, these are what we call one-to-one functions, which means this tracing does not back up and do anything, it doesn't skip around or anything. Each point comes from exactly one t value. All right, and if I want to know what the length of this curve is, one way I might handle that is first by approximating it. And so to approximate it, I'll pull up a new color here. What I might do is just pick a few points along the curve. And approximate the curve with straight lines, because I know how to find the length of a line segment. That's not too much trouble. And each of those line segments I'll say is a part of the length, and we use a lowercase s for length, just following tradition here. And so the length of the curve would be about equal to the length of all these line segments, and we would write this as the sum of all the delta s's. Okay, and I'm leaving off a little bit of the notation here because we're not going to actually compute this sum. What I want to do though is investigate, well, how would I figure out the length of a delta s? Well, that's not too difficult. What I'll just do is take this delta s and split that up into a right triangle. So this down here we might call delta x. That's the change in the x value between this point and this point, just the horizontal change. And this delta y would be the vertical change between this point and that point by way of this right triangle here. And since we have this nice relationship, a right triangle relating the change in x, the change in y, and the change in s, we can compute this. This is going to be equal to the sum of the square root of delta x squared plus delta y squared. And so what are we doing here? Well, this is basically the setup for a Riemann sum. Remember that integrals are just limits of Riemann sums, so the actual length would be given by the integral, and the delta s, when it shrinks to be infinitely small, we call ds, the length differential, and this would range from t equals a to b, because that's the starting and ending point of our curve. But here we see that that is the exact same thing as the integral from t is equal to a to t is equal to b of the square root of dx squared plus dy squared. And that's what happens when the x differential and the y differential get infinitely small. Delta x becomes dx, delta y becomes dy. But I still don't know how to evaluate this because I need to integrate and plug in t values. And so to do this, we're going to take one final step. Up here, what I can do is for each, from this point to this point, I can calculate the change in the t value, and I call that the delta t. So whatever this t value is here, I would increase it a little bit of a delta t value from that t to this t. And so I can exploit knowing that. I'll just factor out a delta t here. So this would be the sum of the square root, and to have a delta t on the outside here, that'd be the same as dividing by delta t squared on the inside. And you can see how this delta t would multiply through, it becomes square when it becomes underneath the square root, and that would cancel with the delta t here, here, and here. So those would all cancel, and this is indeed the same thing as what I started with. And the nice thing is that this becomes the integral from t equals a to t equals b of the square root of, this becomes the derivative dx dt squared, this becomes dy dt squared, and we'll integrate that with respect to t. That dt is not underneath the square root. All right, so now we've got this all together. This is our formula. This is the most important formula, although these will be useful to remember as well. But this is the one we'll plug into for the most part. Length is the x derivative squared plus the y derivative squared, all under a square root. Integrate that with respect to t. Okay, so now that we have our arc length formula coming from these right triangles up here, I can use this to solve problems. Let's go ahead and let's see how this works for a problem where we should know the answer for other reasons. All right, so let's just take this for example. We're going to find the arc length formula to find the length of a line segment. You really shouldn't use the arc length formula for this problem, of course, because it's a line segment. So the real way to solve this problem, one second. Apologies for that. So to solve this problem, the same way, if it didn't tell you to use the arc length formula, would be to just find the distance between 2 points, right? The distance between 2 points, that'd be the square root of -2 minus 2 squared plus 3 minus 0 squared. So that'd be square root of 4 squared plus 3 squared. The square root of 25 is 5. All right, so there's the answer. We don't have to use any integrals to do that. And of course, that's the same thing as just plotting the points, -2, 1, 2, 3, and 2, 0. And the length of this line segment here is 5. Okay, well that's all well and good, but we want to see that the arc length formula works. So let's put that to the test. So we should get 5 as the answer. And let's see that that works with the arc length formula. The arc length formula says the length is the integral from a to b square root x derivative squared y derivative squared dt. All right, so now we need to figure out a parametric equation, because this is for the length of a curve defined by a parametric equation. So for line segments, it's really easy to come up with the parametric equation. We have the formula x is equal to x naught plus x1 minus x naught t. And so for this problem, we have the starting x value, -2 plus 2 minus -2 t. And so that's -2 plus 4t for x. And I want to know what dx dt is, so that's dx dt is 4. All right, and then we'll do the same thing for the y. Y is y naught plus y1 minus y naught t. And then we'll plug in for those values. The y naught is the starting y value, 3, plus, it'll be 0 minus 3, so -3, 3 minus 3t for the y. And that tells me that my dy dt is just -3. All right. Now, last but not least, what are my a and b values going to be? Well, remember, if you're using these formulas here and here, you always use the same starting and ending t values. T is between 0 and 1. That's because we're using the line segment formula. All right, just so you can see, if you plug in a 0, all this goes away, leaving you with the starting x value. If you plug in a 0, this gives you the starting y value. If you plug in a 1, the x naughts cancel, the y naughts cancel. That gets you the ending x and y values. Okay, so that's why we always use these t values. All right, so t is between 0 and 1. Take the square root of dx dt is 4 squared plus dy dt is -3 squared. Integral from 0 to 1, square root of that's 25 dt So that's going to be 0 to 1, 5 dt, 5t evaluated from 0 to 1 is 5 minus 0 is 5, just as we got from the distance formula. But that shows us that the arc length integral seems to be working for us, at least in this case.